Hi guys, wanted to make a new video for you and a bit shorter this time so you don't get a headache, and also it's better to focus on small topics. So last time we looked at A11, and A11 had a long network going to video matrix register and character register. Both of them are used for like selecting which page in the RAM to read from, or room for that matter. But so this was the register, and this is the output of the register, and then finally this is the driver. So for the A11, so there are three drivers, one on the character counter, and there's also one here for video matrix 11. And then down here there was, which is on the same line, I called it A11 out. It's CB11, which is character address 11. So, but that's not all. We followed the white rabbit in quote marks, and we didn't get an answer. So because I needed to also see this enable thing going here, I couldn't see what controlled it. But if you look at DB5 or video matrix address 11, it's a bit more interesting, because here you also have the same enable thing, and if you follow it, so I'm just going to turn off labels for now so don't reveal it straight away. And you have this line here. Sorry, it's this red line. It goes up as the enable. So I've called it the address enable for video matrix. You have three lines that must be high for it to be turned off. Or so when that line here is turned off for the polysilicon, if this one's off, then the output buffer of this register will then take effect and can control this line. Otherwise it's pulled to ground, and it won't work. So yeah, so where does it go? It goes a long way. Another thing, if you follow it, you can see it goes up to the video matrix input. So look, this is the long 40 character video matrix that holds one line of text, and these are data bus inputs. And if you look closely, you can see this one is inverted here, together with some other logic, but finally it goes in here, which again drives this to ground. And you can also see it's a very large transistor, so it must drive a large number of nodes. And so it does, because if you go in, you can see here, it goes in here and into this big network here. And these are, as I said, these are the data inputs. So what I think this is doing is loading data in whenever that line is high. So let's follow it the other way. So this must be high for the address to go high. So let's maybe not so very interesting to follow it, but you can see it goes along all the registers here for the horizontal part. This is the let's see, yeah, okay, we have to zoom in here because, yeah, so it goes further there, but it also goes down here, and it ends up in a connection here. So you have some drivers down here. This is actually a comparator, and that's very interesting, and we will look at that now. So what do we see here? Let's go to the other view. So this is a horizontal crop, because The reason for that is I worked on all these registers. We can turn on blocks here. You can see we have sprite y coordinate register, so each of these here holds I think 9 bits or 8 bits for every sprite y coordinate, and down here it's for x. And you can see these are latches like we had looked at before, and the one to the right is comparator. And what is it comparing? So it's comparing the y coordinate with the counter value, and the counter value is basically the number you get for each line of the raster. So when this one increments to the next line, you actually get a new raster line. And the line we looked at goes into something called yscroll. There you go, yscroll. So let's remove, you can see these 3 bits are yscroll, 2 down to 0. So I have been doing some work on this. You can see from the counter you have some outputs. We call them bit 0, that's the same as RC0, so row counter 0, and so on. And then you have the inverted on the bottom, and then you have 1 and the inverted of 1, and so on. Up to I think 8, because there are 9 bits. There are more than 256 lines on the screen, so sorry for screaming. So basically this is the comparator that compares yscroll. And what happens when the yscroll equals the counter? Well, then you get a badline. So in this timing diagram we have a badline, no sprites, and what happens here is that we get reading of characters. That's very interesting because the video matrix loads characters. These are character accesses. You can see that down here, I think. Access to the video matrix and cologram. So yes, so go back. So this is the line we're talking about. It goes past all of these comparators. So all of these comparators can affect this line. And there's also more. You have a displaylatch, which I've made a video about, so you can look at. It can also affect this line. So if you go in closer here, you can see this is the yscroll register for bit 0. So this is the data bus 0. Can be loaded in here, stored and latched. This is ys0, and therefore up here is the inverted version. This is a clock line, so it can be clocked into the comparator. So I have written numbers here so it's easier to follow. So what do we have here? We have ground here. So to affect this line here, the output of the comparator, we need to have a path to ground. That means ys0 and not RC0 needs to be on at the same time. In other words, they need to be different. And the same goes for the other way. They need to be different. So whenever they are different, one of these paths are active. You can also see that here. So if we have a high on ys0 and a negative on rc0, you get a high on this expression, and therefore the output goes low. That's signified by the bar on top. Or it could be the other way. Again, they are different, just opposite negation. The reason why I have a plus there is because it's not a full expression, because it continues with the IS1 and IS2, but it's the same expression. So now this can be made into a more familiar expression, SOAR, actually. So this is the same as SOAR. So that means if they are different, the output is high, and if they are not different, the output is low. So so therefore this is actually wrong. That's why I need a double bar over there. That's what I've done here. So basically what this means is that if you could compare yscroll with the counter values 3 down to 0, and they are unequal, that's what the bar says, the bottom bar there. I should probably make 2 videos about it, but maybe it's better to just follow me. So so what we see that is when they are different, we want a high out. So because we see that when they are equal, the output is high. When they are different, the output is low. So it's the opposite of XOR. Actually, it should have said XNOR here, but anyway. So when you compare them and they are equal, the expression here is high. But I want it to be low, so therefore I negate it. That's the reasoning. And then you have the displaylatch, which comes from here, this long red line here, up there. Now, when all of these are, this is like a wired OR, so therefore you also have a long bar here. If any of these expressions are active, then the output goes low, right? So this displaylatch can draw it down to ground here also. Now with the De Morgan's theorem, I can make a split on this bar here, and then I can change the operator to AND, and when you split the bar, you get the bar over both of these sides. So this bar goes away, and this negation, which is the same as the bar, just was lazy, also goes away. So what you end up with is that if yscroll equals the counter and the display latch is on, this line goes high, basically. So what do we call this? Let's see. So it goes up here. I don't think I've written here what it means. So you have to go on the other schematic then, and we'll turn on labels. So let's go over there. I basically called it a badline. This is so much easier. So so now, for now on, we call it a badline. So whenever you get to that line, which has this where it needs to draw or access characters, you're on a badline. So, and that makes sense. That the counter is same as a yscroll, and you can also move the yscroll if you want. You just write to it with a CPU, and the badline moves. So the timing changes. So then let's go back again. Now I have the wrong one, this one. So let's go back now that we have this information. What does this mean? We come up here. There's the bad line. It goes up here. This together with some unknown I haven't found out yet, and another unknown with another unknown here. I call it the address video matrix enable. So you can see basically this just inverts it, and then it runs up to that register. Yeah, several ones, because you have VM10 here, then you have VM11 here. So I should write that here actually. So that's it. So this is badline actually. Together with some other logic. I don't know, probably timing of some sort. So probably clock, because we only access what high. So that's what I wanted to tell you. So that's it. To end the video there before I say anything more wrong. Oh, hope you liked it. See you another time. I'll continue to work on this.